Okay, it's our great pleasure today to have Hao Zhang from Tsinghua University to give a talk. And okay. Let me see. And his topic, the topic today is the student and factorization of smooth and nodal conformal blocks in block CFT. Welcome.
Okay. I'd like to thank Professor Wang to invite me to give this talk. The title of my talk today is called solving and factorization of nodal and smooth conformal block in logarithmic CFT. And let me give a brief introduction of the goal of my talk today. The talk is based on the following 4 papers. The first 3 papers is a joint work with Bing Gui, and the final goal of the first 3 papers is to introduce a slowing and factorization property in logarithmic CFT. And there are many applications of this SF theorem. And in my talk, I will mainly introduce the relationship between the slowing and factorization theorem and topological modular functor. And there is another application which relate the pseudo trace approaches and the co-end or end approaches in logarithmic CFT. And in particular, we can obtain the proof of the Gainidov and the Runkel theorem. But in this talk, I will not focus on this part. The next topic in my talk is based on the last paper here. Maybe I think it doesn't work.
Okay, I'll help you.
Okay, the last one. And the final goal of this paper is to prove the non-equivalence of the nodal and smooth conformal block functors in logarithmic CFT, which is not the case in the this equivalence is not the case in the original. And since we are considering the logarithmic CFT, throughout my talk, I will fix C2-cofinite ungraded vertex operator algebra, or VOA for short, V, which is not necessarily semi-simple or self-due. Which means that we will consider the examples like the triplet W algebra, the even symplectic fermion VOA, or even the non-self-due VOA like a WPQ algebra. And throughout my talk, I will not assume the rigidity of the modular tensor category mod V here. The mod V is the representation category of V, or more precisely, the category of grading restricted generalized V modules of V. This is a gradient tensor category, and it is conjectured to be a finite rigid graded tensor category. Okay, to begin with, we have to consider the so-called smooth conformal block functors. Let X be an unpointed compact Riemann surface with local coordinates. The underlying Riemann surface of X is P, and there are n distinct map points on the surface C, denoted by x1 to xn. Each map point xi is equipped with a local coordinate eta I. The eta I has center x9. The smooth conformal block functor is a left design contravariant functor CBX, which is a functor from mod V tensor n to vect. This vect is a category of finite dimensional C vector spaces. The mod V tensor n by a result of Robert-McRae is equivalent to the link product of n copies of mod V. The functor is described as follows. First, we choose a V tensor n module W, And we associate this W to the order mark points x1 to xn, which means we associate each v action yi of W to one of the mark points x1 to xn. Then CBXW, it consists of the linear function of W to C, which are invariant under certain intertraining properties with respect to this ordering. And this CBXW is usually called the space of conformal blocks, or the space of smooth conformal blocks. By smooth, we mean that the axes are compact Riemann surface. We have to distinguish this smooth conformal block functors with the nodal conformal block functors, which is denoted by the conformal blocks associated to nodal curves. Okay, this is our setting, and we cannot describe the precise definition of the conformal blocks here, but you can imagine something like that. It is also very convenient to use the graphical calculus in the conformal block theory, which is really similar to the TQRT theory. The picture for CBXW is the following picture. You can see that you have a genus 2 5-pointed Riemann surface here, and you have a V-tensor phi module W. You associate the V-tensor phi module W to the mark points, and the picture on the left-hand side is denoted by the space of conformal block CBXW. And if you want to reverse the direction of the arrows, you have to replace the modules by its conjugate modules simultaneously, just as the picture on the right-hand side. Okay.
我们看不到那屏幕怎么样？
Okay.
还是没开共享，不好意思。OK， 我说不知道啥要说句话，我不知道在说什么。OK。好。
Okay. Let's continue. In practice, it is often convenient to divide our set of mark points into several subsets. For example, in this picture, we can divide our mark points into blue points and red points. In this picture, we have the genus 2 Riemann surface has 3 blue points and 2 red points. We can associate a V-tensor 3 module X and another V-tensor 2 module Y prime. Y prime means the conjugate module of Y to the blue points and the red points, just as the picture on the right-hand side. Just as what I said before, you can reverse the direction of the red arrow, and so we can identify the space of conformal blocks on the right-hand side with the space of conformal blocks on the to the left-hand side. More precisely, we can view any conformal blocks of this space here as a linear map here satisfying certain intertraining properties. I have to make some description of the Y overlap here. Y overlap is called the algebraic completion of Y, which is defined as the Y prime Q, the space here. More precisely, you can first consider the generalized eigenspace of Y. This is a generalized eigenspace decomposition of Y. Then the overlying Y is just we only need to replace the direct sum by the direct product. You can also view this as the definition of Y overline. So it is convenient to regard the conformal block here and the conformal block here as the same thing. They are just the different expression of the same conformal block.
So for you, a conformal block is a map from
in a priori.
Y prime to C.
Sorry?
A conformal block is a linear map.
In a priori, it is a linear map like this, but it is equivalent to a linear map like this. Because we have to make some composition of the topological category, so it is convenient to consider the conformal block like this. But they are the same thing, just the different symbol for a same conformal block. Okay. We want to consider the higher genus conformal block. So it is necessary for us to consider sorting or composed conformal block. To describe in a precise way, let me pick up X, which is a V-tensor N module, a V-tensor K module Y, a V-tensor L module N, and consider the conformal block phi or n cosine here. Phi is the conformal block associated to the surface on the right hand side or on the left hand side. The cosine is the conformal block associated to the Riemann surface on the right hand side. In this picture, you may regard phi as a linear map from X to the algebraic completion of Y, and the conformal block psi as a linear map from Y to the algebraic completion of M. Then we can define the sorting or the composition of the phi and cosine as the following formulas. This corresponds to the geometry construction of the sorting Riemann surface. More precisely, you can consider the Riemann surface on the left-hand side and the Riemann surface on the right-hand side. And look at the red points of the Riemann surface. You use the local coordinates to cut off a unit disk of each red mark point and glue the remaining annulus to get a Riemann surface of higher genus, like the Riemann surface here, which is a Riemann surface of genus 4.
So what is lambda?
Okay, I will describe it later. Here. So P lambda is a P lambda bullet is algebraically we can define the sorting and composition of phi and cosine as the following infinite sum, where P lambda bullet is a projection map from the algebraic completion of Y to the generalized eigenspace of lambda bullet. This is a projection map. So you can see that each segment is a well-defined element in the algebraic completion of M. But it is an infinite sum, so it is not well-defined in a priori sense. So we have to prove some convergence property to to get a hierarchical conformal block. And this problem is solved in the second paper, in my second paper with Wei. And the result is that this infinite sum converge to a conformal block in the hierarchical conformal block space. So by proving the in order to prove the convergence property, we found a linear differential equation with simple poles for this infinite series. And this method corresponds to the convergence property proved by Yizhi Huang or Yongchang Zhu or Professor Gui. And in our case, we generalized the convergence method to our case. So this is one direction. We want to compose the conformal block or sole conformal block in order to get a hierarchical conformal block. So this is our main method in this slide or in this topic.
Discrete sum or an integral?
You mean this sum? This is a sum in the vector. So you there is a Q parameter here, and we omit this Q parameter by setting each Q is equal to each Q equal to 1, and with argument 0. We prove that this Q series is a convergent series, and in particular, this infinite series.
So is it a discrete series or is it a continuous series? The lambda dot.
It is a discrete series.
It would be discrete.
Yeah, it is a discrete series. And in fact, we omit some Q parameters here. In this slide, we got our Q parameter to be 1. The Q parameter is corresponds to the sewing parameter. Just like when we define the geometric sewing, for example, this is the local coordinate CE or C1, and this is another coordinate pi1. Then the gluing or sewing by constructing the geometry gluing or sewing, we have to use this relation. And in our case, we just choose the Q1 equal to 1 and with argument 1, and use this.
I1, so you have inverse at some point.
Not inverse. Well, why you can consider inverse? Maybe you are. This is the local chart because
from the surface to a region.
Yeah.
And Taiwan is a surface.
Yeah.
So you use the inverse.
So maybe you want to consider something like that, Q1, which is the inverse of pi1. And this is this is just different description of the same sewing relation. We just put 2 local coordinates on one side and describe the relation like that. And for example, in this picture, we have 2 sewing local coordinates.
With multiplication, not composition. That's my question. Is it composition or multiplication?
This is the multiplication, but not composition. Because these are 2 functions, so you can consider them as 2 functions. Okay. So do you have any questions on this slide?
So this theory is convergent in what sense?
Absolutely and locally uniform. Again, we omit some parameter here, Q here, and this convergence is with respect to the local parameter 2 bullets here. And the convergence is like the absolute and locally uniform convergence.
So the conformal blocks are converted with punctures.
Sorry?
The conformal blocks that you define.
Yeah.
Let's say move the punctures.
Move the. Is there anything for? Oh, okay. So conformal block. If you want to remove the, if you want to move the punctures, then the conformal block will vary. So in general, the conformal block will vary with respect to the moduli of the pointed Riemann surface. It depends polymorphically on the mark points.
So the solving is also homework.
Yeah.
Prove that?
It is proved. Because in this slide, we want to make this simple. We want to just consider it as a linear function. In fact, it can be considered as some sections of the conformal block bundle, and which is polymorphic as what you said. Okay, so we can continue to describe one of our main theorem in this talk. And we call it the Soyan factorization theorem 8. The setting is similar to the previous slides. Since we have we can define Soyan conformal blocks, so we can get a linear map from the tensor product of conformal block space to the conformal block space of higher genus. So this linear map is denoted by Sy. As y varies, you can see that Sy is a dynamical transformation with respect to y. And our main theorem states that as y varies, the dynamical transformation Sy is in fact a coen. So we can write the following formula, which states that the coen of the tensor product of the conformal block space is equivalent to the conformal block space of higher genus. And this theorem has been proved in some special cases for lower genus. For example, in genus 0, this theorem amounts to say that we have the associativity property in the tensor category, which is due to Huang-Lepkowski jump. And in a more general setting, this theorem is given by a recent paper in Moriwaki.
What's the meaning of more general setting? What is it?
They consider some VOA which is more general than the C2-cofinite VOA. But they he focus on the genus 0 setting. Yeah. Okay. So this is one of our formulation of the Soyan factorization theorem.
I have a naive question.
Yeah.
So go back to this lambda here.
Yeah.
There's like labeling there these long completion, right?
Yeah.
They are like the highest label whatever, but you said you're considering C2-cofinite, so that means that's like a finite.
No. This is a direct sum, but this is an infinite direct sum. Oh. But each graded space is finite dimensional. Okay. And this is guaranteed by the condition for the grading restricted generalized V module. And this is not guaranteed by the C2-cofiniteness. And since all modules we are considering in this slide is grading restricted, so each space like this is finite dimension. Okay.
C2-cofinite means there are finitely many symbols.
This is one of the properties C2-cofinite. But he can guarantee much more. Okay. And one of the most important theorem that needs the C2-cofiniteness is this theorem. We need the C2-cofiniteness to derive the differential equation in a finite dimensional space. So this theorem heavily uses the condition C2-cofinite, this convergence theorem. Okay, this is our first version of slowing and factorization theorem. And this theorem is not very useful in some practical sense. So we have to give another formulation which involves the notion called the fusion product and the canonical conformal blocks. The notion fusion product is inherited from the Zhang fusion product in the tensor category. And our fusion product is just a generalization of their fusion product. Let me define the fusion product in this slide. In this page, we fix V tensor N module X and point the Riemann surface X here. And this X has N incoming points and K outgoing points. The N points are the blue points and the K points are the red points. We associate the V tensor N module X to the blue points of X and this conformal block space. This conformal block space will give lefty that linear functor from mod V tensor K to the vex, which is the category of finite dimensional C vector spaces. And since every lefty that linear functor from a finite C linear category to vex is representable, we have the following Y-natural isomorphism. Roughly speaking, we have a V tensor K module here, which represents the conformal block on the right-hand side. And this unique V tensor K module is called the fusion product and written as fusion X here. And this is our fusion product. And if you choose Y equal to fusion X in this isomorphism, then the home space on the left-hand side becomes an anamorphism space and fusion X. And the identity map in the anamorphism space corresponds to a conformal block on the right-hand side. And this conformal block is called the canonical conformal block. So to summarize, you only need to memorize that fusion product is just an object and is an object that represents the smooth conformal block functors. And the canonical conformal block is just corresponds to the identity map. Okay, this is our fusion product. Later on, I will give some examples of fusion products, but not now because I want to go directly to the next formulation of our slowing and factorization theorem. Recall that we have the canonical conformal block of this conformal block space. With the help of this canonical conformal block, we can give our second formulation of the slowing and factorization theorem, which involves the fusion products. This says that the linear map given by composing the canonical conformal block gives an isomorphism from the lower genus conformal block space to the higher genus conformal block space. And this isomorphism is called the slowing and factorization isomorphism, or FS or FF isomorphism for short. You can see that roughly speaking, this theorem tells us you can replace the red part of the higher genus conformal block space with the fusion product associated to the red part. For example, in this part, this fusion product is just the fusion X here. You can see this picture. So this theorem gives us a practical approach to reduce the genus of a conformal block of higher genus conformal block space. So this is our formulation of the second Fourier factorization theorem. Do you have any questions? Okay. So in order to help you understand this better, I will give some examples and show that the Y Fourier factorization theorem A implies the Fourier factorization theorem B. The proof is quite simple. You just write by the Fourier factorization theorem A, you can write the higher genus conformal block space as the coend of the tensor product of lower genus conformal block space. And by our definition of the fusion product, you can identify this conformal block space with this home space. Then, by a result due to Lomachenko and Fuchs and Schreiber, the coend of the home functor and another functor is equivalent to their composition. So we can identify this coend with the lower genus conformal block space. So the proof why Fourier factorization theorem A implies the Fourier factorization theorem B is quite simple. You just use some known theorem to give the proof.
And also, so you use this representativity result.
Yeah.
Which tells you that there's this fusion product and you got to think that some of this, but you can also do that in conformal block.
Yeah, of course. You mean the right conformal block is this conformal?
Yeah.
Of course, you can. This is just symmetric, right? Of course, you can replace the conformal block on the right hand side. If you something.
So because here you're using the fusion product of two genus.
Yeah.
Surface.
Yeah.
But the guy on the right is only one genus. So
yeah, of course you can do that.
Does it from you like do this like a shrink one genus, shrink another one? That's the same as shrinking two.
Yeah. Of course, and this I think this corresponds to the third formulation of the Fourier factorization theory. I will give this later on.
Okay.
Maybe I can give this here. There is in practice we can draw a picture here, and by sewing we can sew this to surface to get a genus 4 surface. And there are many mark points. I forgot the mark points number. Oh, there are 3. And there are 2 ways to get the fusion product. For example, you can associate X to this Riemann surface, and you can get a fusion product of the, for example, this is called X, and this is called Y, and this is called the sewing of X and Y, which is geometry. And we can have the fusion product here, and there is another way to get a fusion product. There is a fusion product coming out of the outgoing point of X, which is here, and you associate this V tensor 2 module to these two mark points, and there is a V tensor 3 module coming out of the outgoing points here. And these two are isomorphic. And the canonical conformal block is just, this canonical conformal block is just obtained by composing this and this. So this theorem is equivalent to the following factorization theorem B. Oh, okay. Okay. Let me give you some examples of fusion product, because fusion product is quite abstract. So we want to make some precise formulation in the lower genus case. The first example is the Huang-Lepofsky-Zhang fusion product. In the VOA tensor category theorem, we can consider two V module and consider their fusion product defined by Huang-Lepofsky-Zhang. This fusion product will give rise to the tensor category theory of the VOA. And if you lift your Huang-Lepofsky-Zhang's fusion product to the link product through copies of mod V, then you will get this fusion product, and which is also denoted by the fusion HLV. And this fusion product is just corresponds to this picture. This picture is like the zero surface with two incoming points and one outgoing point. And for each V tensor 2 module associated to the incoming point, the module coming out of the outgoing point is just the fusion product we considered before, and this is exactly the fusion product of Huang-Lepofsky-Zhang. And if you reverse this picture and consider the picture consider genus 0 picture with 1 or 0 incoming points and 2 outgoing points. For example, in this picture, we consider 0 incoming points and 2 outgoing points. And we associate a V tensor 0 module, which is equivalent to the vex, the category of finite dimensional vector space. And you associate V to the 0 incoming point, and the V tensor 2 module coming out of the outgoing point is isomorphic to the N or the co-evaluation objects in mod V tensor 2. And you can see this is the end, not the coend. And this tensor product is over C, not the VOA's tensor product. So in a priori, this X tensor X prime is a V tensor 2 module, not just a V module. This end object is usually considered in the diagonal CFT, and in some tensor category or some T2FT people's paper, they use this object to define the topological modular functor. For example, in Lucas Loic's paper or the Lucas Muller's paper, they consider some object which is similar to E here to define or to construct the modular functor in the Grothendieck Verdier category. And the third example is the Liu-Barthélemy construction L, which is defined by the composition, which is defined by applying the HLV product to the co-evaluation object E here. And this L is a V module, and this by this theorem we just stated before here, this is usually called the transitivity of the fusion product. By the transitivity of the fusion product, this L this geometrical construction L is isomorphic to the fusion product associated to the torus with 0 incoming points and 1 outgoing point. The fusion product associated to this picture is isomorphic. And so what's the relationship between
L is a Hopf algorithm using this.
this is a long story. This is not easy.
But if I try to prove or not.
We can prove that, but it is a really complicated story. The whole algebra structure is easy, but the algebra structure is not. And we plan to write some papers about the proof algebra structure of L, but it is not. I cannot.
So one comfort torus is the Hopf algorithm.
But yeah.
You use it.
Yeah, we use this, but there are some in practice. Maybe we can talk about this later on. And in the self-field and the rigidity case, by the way, if this self-field, then the mod V is conjectured to be rigid. So, but this conjecture is not true, so we have to assume this. And if these conditions are all satisfied, then the mod V is a factorizable finite category. And in this case, L is isomorphic to the usual Logarithmic coefficient here. Because you can identify this n with a coefficient and the tensor product or the fusion product commute with the coefficient, so you can
change and the coefficient becomes outdoor.
Yeah. But in our case, our case is corresponds. I think it corresponds to the Grothendieck-Verdier category, so you cannot just change the order. Okay. This is some examples of the fusion product. What kind? Okay, this is too late.
It's okay, we can go over.
Okay. So our first application is the self-folding picture via the end E. Recall that in the previous page, the end E is the fusion product of D associated to the inner 0 sphere with 0 incoming and 2 outgoing. And we let omega be the canonical conformal block of this fusion product. Then the composition by composing the canonical conformal block omega, we get the Tholen factorization isomorphism from this space to this space. And this picture corresponds to the usual Tholen factorization isomorphism, which is given by Damiolini, Gibney, and Carafta in the original CFT case. So in a word, you can view our Tholen factorization theorem as a generalization of their result to the logarithmic CFT. In a word, you can replace the red part by the end E to get this picture from this picture, which is the genus of this picture is lower than the genus of this picture. To summarize, factorization of the smooth conformal block functor here is given by the end E here. So I want to compare the smooth conformal block functor with the nodal conformal block functor. So we have already obtained many results of the smooth conformal block functor. So I can write something here. So our strategy to deal with the smooth conformal block functor is called the Tholen factorization theorem. And the objects we are considering in the smooth conformal block functor here is called the fusion product thing. or the and E. The and E. So this is what we want to say about the smooth conformal block functor. Another application is the connection of the topological modular functor. Recall that we already talked about the Liu-Bach-Stringholt construction L, which is a V module associated to the torus with 0 incoming and 1 outgoing. Let alpha be the canonical conformal block associated to this fusion product. Then the linear map by composing alpha gives the Sawing and factorization isomorphism from this conformal block space to this conformal block space. Again, we can replace the red part by the fusion product of the red part, which is L, the Liu-Bach-Stringholt construction. So a simple corollary of this theorem is that we can identify the space of conformal blocks for an n-pointed smooth Riemann surface with genus G to this home space. This proof is quite simple. You can just draw the picture like the G handles, which handles correspond to one genus, and you can replace each genus. Then you can identify a genus G surface with a genus 0 surface, which corresponds to the home space. So the proof of this theorem is just a simple application of the Sawing and factorization theorem. Okay, let me go into the comparison between smooth conformal block functor and nodal conformal block functor. So to begin with, I want to go over some history about the factorization of conformal blocks in the rational CFT case. And we review how algebraic geometers obtain factorization of conformal blocks by infinitesimal smoothing of nodal conformal blocks in the rational CFT. So in the following two pages, we assume that V is ungraded C2-cofinite and rational. By rational, we mean that the category is semi-simple. In the following 2 pages, the history is like that. For in the Virasoro algebra or Virasoro VOA case, in the Virasoro VOA and higher genus case, the factorization is obtained by BIMSA-Tsinghua and Mazur in the 90s. For the affine algebra higher genus case, the factorization is obtained by Tsuchiya, Yamada, Backlog Kirov, and Wu Yanga. And for the general VOA in the genus 0 case, the factorization is obtained by Nakatomo and Tsuchiya. For the most general case, for the general VOA and higher genus, this result is obtained by Damiolini, Gibney, and Terrasca in 2019. And in my slide, I want to use the setting of Damiolini, Gibney, and Terrasca to give an introduction of how algebraic geometers obtain the factorization. They just do the following procedure. First, they generalize the definition of conformal block to the nodal curves. You can see that we only define the nodal the conformal block on the smooth curve. They say that we can generalize the definition of conformal block to the nodal curves. Then they observe that it is easy to prove a factorization of nodal conformal blocks. And the factorization of nodal conformal blocks is given by irreducible modules. Their results is just this picture. This is a nodal curve. And the higher genus nodal curve picture, the higher genus nodal curve conformal block is isomorphic to the direct sum over irreducible modules of the lower genus smooth conformal block. And they consider the infinitesimal smoothing of this isomorphism. And they use the infinitesimal smoothing to prove that the spaces of conformal blocks, no matter smooth or nodal, form a vector bundle over the MGN bar, which is a compactified moduli space. The most important part of the vector bundle structure is that whether the dimension of the normal conformal block is equal to the dimension of the smooth conformal block, because the most difficult part is the boundary of this moduli space. You have to prove that the dimension will not change when the surface goes to the boundary. In particular, use the locally free or the vector bundle structure. They obtain the factorization of the smooth conformal block given by reducible modules. You can just imagine that they smooth this Nodal curve to get the smooth curve.
This isomorphism is by definition, or what?
This is not just straightforward, but it is.
You have to define this right first. You have to define
no, this is not the definition. So the definition is the definition relies on the normalization, but this is the normalization, but this is not quite straightforward. The definition is just of this definition like that.
No. So they first proved this isomorphism.
Yeah.
Or other people proved this isomorphism.
Oh, they first proved this isomorphism.
They first proved this isomorphism.
Yeah. And this is also proved by.
I have a question regarding like the compactified moduli that you have there. Like you did mention that like on the boundary, like you have to ensure some regularity because you're thinking of the CPU, like it's frictions of the vector bundle or light bundle, I guess.
So the proof is a vector bundle.
Yeah, they prove that this is a vector bundle.
So you have one that way, you have a vector space. You have to prove that it's a vector bundle.
Yeah.
Right,
the most difficult part of this proof is whether dimension is not.
At the bundle. Okay.
Yeah.
Because so like
coherent shift enough time.
right, yeah, exactly. So I'm wondering, like the guy on the left, right, which is we just defined. Yeah, for that equation, the guy on the left.
Yeah.
Each of those guys, you can define it as vector bundles over nodal curves.
Yeah.
And on the right, I'm wondering, like maybe you should throw away certain badly behaved conformal blocks or something like that to get that result or something like that. I'm wondering how you actually prove the.
You mean how to prove this?
Yeah, how to prove that you.
Yeah. They prove. I think they use the so-called infinitesimal smoothing used some formal power series method, because they just consider something similar to this smooth picture as the formal power series picture, and with this intermediate thing, they just get this theorem. This is a little complicated. Their proof relies on they call it the sewing theorem, but the sewing is not quite related to the sewing we are talking about. So it is hard to discuss the proof in my talk. And the so-called sewing is just some kind of formal power series approach to the smooth picture.
Or
So I think they're explaining according to the singularity. Right?
Yeah.
You have one singularity, two singularities, stuff like that.
And also like the connection width of the throw. I mean that's firm trying to achieve.
Yeah.
Yeah. So I think as you said, like it's a power series argument, so you can't have
Yeah.
Okay.
Yeah, it's something like that.
Okay.
Yeah. Okay, so this is the rational CFT case. So we are now we are now again return to the assumption that V is ungraded and C2-cofinite. We remove the assumption rationality here. In this picture, it is not hard to get the nodal factorization. This is the nodal factorization in the logarithmic CFT case is obtained by Damiolini, Gibney, and Krashen in 2022. They introduced a notion called the mode transition algebra A. This is a priori an object in mod V tensor 2, and this is defined by two-sided induction of the true algebra. Later on, they prove that this is an associative algebra. But in my talk, I only need the mod V tensor 2 module structure, not the algebra structure. We only need this structure. And they prove the following theorem, and we call it the factorization of the nodal conformal block. Their theorem states that we have the isomorphism between the smooth conformal block space, which is related to the mode transition algebra A here, with the nodal conformal block space of higher genus on the right-hand side. So to summarize, their theorem just states that you can replace this red part by the mode transition algebra A here. You can see that in the logarithmic case, irreducible V modules is not enough to consider even the nodal factorization. So they introduce the mode transition algebra, which is related to the two algebra. So we can describe genus zero conformal blocks via the end and the mode transition algebra. We apply the theorem of DGK to the genus zero case. Then we can get this factorization of the genus zero conformal block. You just replace this nodal part by the mode transition algebra A to get a smooth conformal block and identify the smooth conformal block with its home space here, which is a home space in the mod V tensor 2, the category mod V tensor 2. On the other hand, we can consider the zero conformal block space here. Then this space is isomorphic to the home space, which is well known. And by results of Fuchs, Froman, and Schreiber, this home space is isomorphic to the home space involving the E. You can see that these two spaces are really similar. If you can prove that the A is isomorphic to E, then this two space, of course, has the same dimension as you wish. But unfortunately, this is not always the case. So in the rest of my talk, I assume an additional assumption. Let V be a C2-cofinite ungraded VOA, which admits a module that is not generated by its lowest weight subspace. Many VOA satisfy this assumption. For example, the triplet algebra and the symplectic Fermion VOA. In this assumption, we prove that there is two V modules X and Y in the mod V, such that the smooth conformal block space and the nodal conformal block space have non-equal dimensions. By propagation of conformal block, we can add extra points with vacant input to the space without changing the dimension. Then, so we can conclude that the spaces of conformal block associated to X, Y, V do not form a vector bundle on the M0 N bar for N greater or equal than 4. So the conformal block structure is no longer valid in the logarithmic case, or in the genus zero logarithmic case. Because the definition of this modular activity is some kind of stable curves. You need the n greater or equal than 4 to get an existence of for example in n equal to 2, this space has no stable curve. And for n equal to 3, this space has only one point. So we need at least 2 stable curves. So we need n greater or equal than 4. We can make the choice of x and y in a more precise way. In the proof of above theorem, we in fact choose x to be an indecomposable projective field module that is not generated by its lowest weight subspace, and y to be an indecomposable projective module or irreducible modules. More precisely, if V is a triplet algebra, we can choose x to be the projective cover of x1 minus, which x1 minus is the unique irreducible module with maximal conformal weight. So we just use this projective cover to prove our theory. And a simple corollary is that we can deduce that the end E is not isomorphic to the mode transition algebra A. Recall that we have the true isomorphism. And these two spaces, we prove that these two spaces have non-equal dimension. So it is impossible that this E is isomorphic to this A. So we conclude that the end E is not isomorphic to the mode transition algebra A in mod V tensor 2. And this is a question asked in a recent paper of Danielini and Voigt. They asked that what's the relationship between B and A, and this is one of, I think this answers partially of their questions. In this case, we just give a negative answer. In this assumption, we just give a negative answer, and so we answered partially of their questions. Okay, that's all for my talk. Thank you so much.
That's all done. Are there any questions? So which one is bigger? So which of the space is bigger?
You cannot see this from my proof.
You can only show that they're not equal.
Oh yeah.
But you cannot compare them. You prove them.
Yeah, this is another question. This is another question.
Okay. So how do we prove they're not equal?
In fact, we can show that we can give some phenomenon of why they are not equal, because you can see that by the definition of the mode transition algebra A, it is obvious that A is as a left V module generated by its lowest weight subspace, and E is not generated by its lowest weight subspace. Because if E is generated by its lowest weight subspace, then all modules are generated by its lowest weight subspace. We can use some argument to prove that.
So by assuming that plane, then you get some quantity.
Yeah. We use in my paper we use some we have some argument that if such dimensions are equal, then we get some isomorphism between some modules. And on the one side, the module is generated by its lowest weight subspace. On the right hand side, the module is not generated by this kind of argument. And the argument needs some projective cover also.
So you don't expect the thing that's not generated by the lowest weight subspace.
We
do expect this is bigger.
I think there is some result which says that which one is bigger, but I have to check down.
Yeah, it seems that E is bigger than A.
I think
Maybe A is the reflect of E.
yeah, I think but I have to check some this ratio, I think. And I expect that all C2-cofinite ungraded VOA has some project which is not generated by example. I think that we can remove this condition because this is always true. I think I conjecture that this condition is always true under this assumption. Oh, we
Rational. What about rational?
not rational.
Yeah, so you have to say that if V is not rational.
Yeah.
So if V is rational,
Yeah.
right?
Yeah.
So if you think that
Yes.
if V is not rational and C2-cofinite and ungraded, so
Yeah.
then you want to say that it's
Yeah.
not.
Yeah.
It's model.
Yeah. Rational VOA, of course, the condition is not.
You can prove that.
Okay.
Okay.
So is it easy to say what is on you just said it's
I think their characterization use some kind of universal algebra is something like there is a true algebra. You consider true algebra as the two-sided algebra of the universal algebra of 0 degree. Then you can consider the AV as the maybe as a two-sided module of this. Then you can use the induction to define the A. Roughly speaking, if you want to define the A in an algebraic way, then it is the algebra like this. Maybe you have to consider the two-sided induction. I have to write the tensor 2 here. And in fact, in my paper, you can we say that you can just define the A to be the V-tensor 2 module that represents this conformal block and show that this is lowest generated. So in my proof, we only need the fact that the A is lowest generated. So we don't need the general construction of the mode transition algebra A from the two algebra AV. We only need the fact that it is lowest generated. So we can just define the A to be the module that represents this Nodal conformal block. And all our proof will go on using this.
This A or V is
A and V is the true algebra.
Okay.
So if it's C2-cofinite, it's the finite dimensional algebra.
Oh, yeah, it is a finite dimensional algebra.
I see.
Okay.
So do you know like the physical interpretation of this condition?
C2-cofinite.
No, the fact that you don't admit a module that's generated by the lowest.
Physical concept. Sorry, I don't have the patient.
Okay, so that's time again.